Just like the other branches of mathematics, applications of integral calculus can also be approximated. Check out how the first method works. Welcome to Numerical Solutions to C Problems. Before delving on the different methods, let's compare analytic and numerical integration in solving for areas. Say a function describes a curve and the area under is bounded by a and b. Exact integration utilizes integral strips with dimensions of y and d of x. The total area is then the integral of y dx or f of x dx from a to b to solve for the exact area. On the flip side, numerical integration then adopts the same concept of working with strips, but this time, the number of strips are provided instead of integrated. The area of each strip is solved and the summation is taken. The first method of numerical integration is called midpoint rule. With the task of looking for the area below a curve bounded by the limits a to b, a desired number of intervals should be provided. These intervals also stand for the number of rectangles comprising the total area. The dimensions of the rectangles are necessarily determined to take the area. The base is tagged as delta x, and delta y takes the height by using the midpoint of the interval. With base and height already known, individual areas are solved and added to have the total area. This is shown from Raymond's sum. This method is simple to do, but it shows inaccuracy in the exact area computation. In identifying the area of individual rectangles, why do we need the midpoint? If we take a single strip under the curve and we are to determine the dimensions to solve for the area, it is easy to take the base or delta x. But since the top involves a curve, the height is compromised. One case is to take the height at the left part, which then creates an area short of the required value. At the same case, if the rectangle's height is taken from the right, there would also be an excess area added. In order to minimize such area deviations, the height of the strip is taken from the midpoint of delta x. From Raymond's sum, delta y is labeled as f of m sub I. Having a closer look at the top, the excess on one side compensates the space on the other. With the dimensions clearly labeled, the area is then taken as delta x times the y midpoint. And the total area is the summation of delta x with the midpoint y from the first rectangle to the last. With the concept already laid out, the area below a certain curve can be computed without using the integrand. However, the solution might take time if areas of individual strips are computed. Say we have a curve and its area is subdivided into 6 strips. The area of each strip is to be computed, making the total as the first strip plus A2 and consequently A3, followed by A4 with A5 until we have A6. To simplify the total, each area can be computed as delta x with y1 added with delta x of y2. There are delta x of y3 and also delta x of y4 with delta x of y5 until delta x of y6. Delta x is common as the intervals are taken regularly by division. To simplify the solution, extract delta x and get the total area as delta x times the summation of all the y's from y1 to y6. A short example of the method involves the area below the curve described by the integral of 2.5 x squared plus 3.75x plus 1. The area is bounded from 0 to 1.2, and the solution requires 4 strips. Using the limits, the total base of the total area is then 1.2 less 0, which is 1.2. This base is divided into 4 intervals, giving delta x as 1.2 upon 4, or 0.3. So the middle x coordinates are taken as 0.3, 0.6, and 0.9. To solve for the height of each strip, take the midpoint, making 0.15, 0.45, 0.75, and 1.005. These are the values to use in the function in order to look for y. y1 is then computed as 2.5 times the square of 0.15 plus 3.75 of 0.15 plus 1, simplified as 1.61875. y2 needs to plug x of 0.45 into the function, making 2.5 of 0.45 squared plus 3.75 times 0.45 plus 1, which is 3.19375. y3 is solved by placing 0.75 into the function. That is 2.5 with a square of 0.75 plus 3.75 times 0.75 plus 1, giving 5.21875. y4 is solved similarly. 2.5 times 1.05 squared plus 3.75 times 1.05 plus 1, giving 7.69375. The total area is the base of 0.3 multiplied by the summation of the heights, which are 1.61875, 3.19375, 5.21875, and 7.69375. This is solved as 5.3175.